Imagine being in ancient Egypt, and you are asked to build the biggest pyramid. How can you proceed to verify its size? In today's video, this is what we will study. But how can we actually do that? The answer to that is in triangles, a shape that seems basic, but that can be found everywhere in our world. A triangle is a polygon with 3 sides, 3 points, and 3 angles. And they were already known in Babylonia 2000 years before Christ. As I said earlier, triangles are everywhere. Hexagonal crystals, like quartz, are shaped with triangles. And as in biology, we can find vegetal cells with a triangle-like shape. This is done to optimize the distribution of the nutrients. And humans also use triangles to build pyramids, for example. To understand them more, we would need to look at their properties. Even if they are different, they share the same properties. For example, the angles in a triangle will always add up to 180 degrees. This is demonstrated down below with the alpha, beta, and gamma angle. Knowing this, we can use that information to deduce the value of an unknown angle. In this example, we have a 60-degree angle and a 40-degree angle. Gamma's value is unknown. We know that alpha plus beta plus gamma is equal to 180 degrees. We will substitute the values and solve the equation. We then get that gamma is equal to 180 degrees minus 60 and 40. So gamma is equal to 80 degrees. Now here is an exercise. I will let you try to deduce the value of gamma. If you need to, you can pause the video. So to solve this, we have to remember our formula. We'll replace the values and do a subtraction. And here we get that gamma is 60 degrees. We can now write that gamma is 60 degrees and have all the angles in the triangle. There is also an interesting fact that is worth knowing. In a triangle, the largest angle will always be opposite to the biggest side. To test if you understood that correctly, look at this triangle and try to find the biggest angle. You can, again, pause the video. So looking at the 3 centimeters side, we can tell that the biggest angle is 71.575 degrees. Let's try again, but this time we will only know the angle and we will have to find the longest side. So if the biggest angle is 80 degrees, the biggest side will be the bottom one. We talked about similar properties, but we'll see that triangles are classified based on their properties. We first have the arbitrary triangle. It is the most basic one and has no notable properties. It can be one of the other types of triangles, but we generally make it undefined. We then have the isosceles triangles. They have 2 equal angles and 2 equal sides as shown down below. Here B and C have the same length, as well as alpha and beta are equal. Then we have the equilateral triangle. All of its sides have the same length, and all its angles are equal. A is equal to B, who is equal to C, as well as alpha is equal to beta, who is equal to gamma. Finally, we have the right triangle. It is a triangle who has one angle equal to 90 degrees. The largest side is C, called the hypotenuse. Let's practice a last triangle exercise before diving into the heart of the subject. Based on the values shown, can you tell what type this triangle is? It is, of course, a right triangle because of the 90 degrees angle. But how does that help us for the pyramid problem? Let me introduce you to the most known theorem in the world. It is called the Pythagorean Theorem, and it has the name of Pythagoras because his group wrote the theorem. The Pythagorean theorem states that the sum of the squares of the lower sides is equal to the square of the biggest side. Unfortunately, it only works with right triangles. The formula of the Pythagorean theorem is given by a squared plus b squared is equal to c squared. To understand that concept, we need to visualize directly the concept. Remember that a square. Here is our visualization knowing that the squares have as area a side squared. Now let's use that theorem, should we? We will manipulate the formula to get the length of the hypotenuse. So let's use the formula we previously had. We take the square root of both sides to cancel the exponents. Since it cancelled, we get a plus b equals c. Now let's use it in a real situation. We have a right triangle with sides 3 and 4 and an hypotenuse of c. We substitute the value of a and b. We get 3 squared plus 4 squared equal to c squared. If we simplify, this gives us 9 plus 16 equals 25. We cancel exponents with the square roots and we get that square root of 25 is equal to 5. So c was equal to 5. We can also reverse the theorem to prove a triangle is rectangle. This time we have all the value and we will have to verify the equation to prove the nature of the triangle. By doing the same method, we get that the hypotenuse is equal to 13. The triangle is then a right triangle. But then a question must be asked, what would happen if we push that to the extreme? To have some context, in last video we talked about exponentiation, which is a repeated multiplication. For example, x squared is x times x to the third power is x times x times x. 2 squared is equal to 2 times 2. And 4 to the third power is 4 times 4 times 4. We can also find the original number before it was squared, thanks to square roots. If we take the square root of x squared, it will simply return x. For example, the square root of 4 is 2. But why is it so important? Well, sometimes the result may be infinite, to the point Pythagoras' disciples killed themselves. To understand, let's do a square with side 1. And we will calculate the diagonal of that square. If we think about it, we'll notice a right triangle, and this will allow us to use the Pythagorean theorem. Using the Pythagorean theorem, we get that the diagonal is equal to the square root of 2. But what is its value? Well, the square root of 2 never stops. It is approximately equal to 1.41 for 2135, etc. It was the first number discovered that you could not describe with a normal fraction. And for the Pythagoreans, it was an aberration. They always thought that numbers were rational. We can note that the square root of 2 is inside the real set. And as I said in the previous video, rationales can be written in fractio are used to represent numbers between integers. But mathematics has always a way to reward you when you find iteration in something. Remember when I told you the square root of 2 could not be rational because of its chaotic sequence? Well, what if we made the fraction infinite and forced it to approximate the value of our irrational number? We get 1 over 2 plus 1 over 2, etc., and the further we go, the closer we are to the value. The process we just used is called a diaphantic approximation. It consists of trying to express irrational numbers with integers and rationales. But how can we be sure that the square root of 2 is irrational? Well, there is a method called the proof by contradiction. It consists of assuming the opposite of what we are trying to prove to find a contradiction. To start off, we will assume the square root of 2 is rational and that it can be written as a fraction. This would mean that the fraction is at its lowest form and that they cannot be simplified. We solve the equation by cancelling the square root. This gives us 2 equal to p squared over q squared. But doing this implicates that p and q are both even, so that they can be divided by 2. This means the fraction can be simplified and contradicts the fact that the fraction could not be simplified anymore. Therefore, the square root of 2 is irrational, as we proved it. There are, of course, other methods for proving that we'll cover later. So here is the end of the video. I hope you liked it. Don't forget to like and subscribe. See you next time.